Good morning, students. And today we'll be working on machine translation with transformer. So the transformer is actually very a popular architecture even until today, right? So the transformer is actually based on the idea of attention mechanisms, right? So in the previous lecture, we look at attention mechanisms, right? But what transformer excluded is that it wants to only use attention and not anything else, right? No convolution, no recurrent neuron layers in here. So the question is how, if you only use attention, how are you gonna capture sequential information, right? Because in recurrent neural network, you assume that by sharing the network, it can carry forward the sequential information. For convolution, it's assumed that by convoluting several tokens together, you actually try to capture the relationship between different tokens, right? As for a transformer, Walt, it proposed that if you add the positional encoding, then it can firstly better capture sequential information, and then by employing multi-head attention, which is simply a linear projection of different tokens with another different tokens pairwisely, then you can capture the relationship between each of the tokens pairwisely, right? So that's the idea, right? So transformer has this encoder thing, and then the encoder will capture the information and flow it into the decoder, in which it will flow as the query, the values and the key, and the decoder will take the outputs, go into the mass multi-head attention, and then forward it into the as a queries through this attention. And then basically it's trying to say that, hey, if this is the query and this is the value and the key, what would be the information that would be important here for decoding this word, right, as a query, right? And then finally it will softmax and output the word. But what's so special about transformer is that because it's very each of the component is very independent, it can be very well parallelized, right? Then it can run very, like, with a lot of GPU. It can the performance can scale up very quickly, right? So that is probably the major contribution of transformer. Yep. Without further ado, we're gonna code, and then hopefully you guys can gain more understanding aside from the theoretical aspect that you guys learned in the lecture, right? So let's take a look at what we're gonna do today, right? So we're gonna load some data sets, and I already prepared some coding, so we don't spend too much time on here, and to make sure our tutorials stay within 1 hour, right? And then we also have EDA, same code like last time. We're gonna have pre-processing, which is tokenization and vocabularies, and data loaders, right? Same. So basically in 1 to 4, we are just simply repeating the same thing. And but in section 5, we'll be actually coding the models, right? In which I have prepared a lot of structure in which we're gonna code, right? As for training, tests, and attention, they are basically the same code we have developed in the previous attention lecture. All right, so mainly we're gonna just code number 5. All right, so let's run this code. If you have GPU, you can always run this, and this is my torch version and torch text version. For the loading data set, I will be using the same multi-30K data set. For the EDA, we're gonna again run as an example, and we're gonna make the data set smaller here into train size, validation, and also the testing set. All right, and for the pre-processing, this is basically the same code we use in the previous lecture, right? In which we have 2 tokenizer for each language. And we also have, so this is an example. And we have 2 token, we develop this field function U tokens for building the vocabs later on. And based on the 2 tokenizer, we're gonna have 2 vocab transformation. And here's some example, some mapping back. All right, so we're not going to talk too much about this because we did all this in the previous tutorial. And then here is the data loader. Same stuff. We have the sequential transform in which what we do is we first concatenate SOS and EOS, and then we numericalize them. And then finally, we transform them into PyTorch tensor. Yep. Notice that in this collate batch, we actually return the source length as well. Yep, because it will be used for the transformer as well. Here's the data loader, and shuffle is false for validation set and testing set. And here's simply the batch size and the sequence length for every time you load the batch. All right. And I just put it here to make sure that if I run everything, it will stop here, but I'm just gonna delete this. All right. So I think now we are ready. We can close this now, and we are now ready to actually work on the model, right? So the first part we're gonna actually work on is the is the encoder layer, right? Which is the gray part here. And then later on, we're gonna work on the encoder, right? In which we're gonna actually repeat this multiple times, right? All right. And so starting with the encoder layer, right, which is the gray part here. So I already have prepared some of the code, right? So we start with the class of encoder layer, and then the module, and then we have a couple of parameters we have set, right? So the hidden dim is basically the hidden dimension we're going to use in this encoder layer, right? Number of heads, right? So so in this multi-head attention, we have to specify how many heads we actually splitting this input into, right? So the PF this is basically this feed forward dimension, right? And the dropout is basically simple dropout, and the device is whether we are using CPU and GPU, right? All right. So we are done here. Now let's code some so we can gain more understanding how this actually look, right? And then in the encoder, we can actually actually write the whole thing that use the encoder layer, right? All right. So in the encoder layer, there's several things we have to code right here. The first thing is the self attention. Let's do it like this: attention layer non equal to nn dot layer non hit them. All right. So this layer norm is basically referring to this norm, all right? So you may wonder, what is this layer norm? Well, it's just a basic normalization procedure, right? To make the numbers smaller so that your convergence is more stable, right? A convergence procedure, yep. And then self.ff. Similarly, we're gonna have for, and then the layer norm, hit them, right? So this is for this one, and this ff is basically for this one, right? And we're gonna make it very nice. And then of course we have to make sure that when the input is done, we're gonna put it into this cell, this multi-head attention, right? And also this feed forward, right? So we're gonna have self attention is equal to multi-head attention. We haven't coded this module yet, all right? So and we have to pass in the hidden dim, end heads, and dropout, and the device. All right. So this is something we haven't coded yet, but we're gonna implement this below, right? In which you're gonna take the input, go into this module, and do something, right? The next thing we're gonna do here is self.feed forward, and this is feed forward. It's basically equal to position feed forward layer, hit them, and PFM. And this one is just referring to this blue layer, right? It may look very scary, but actually it's just a linear layer, yep, that project hidden dim to PDF to PD dim, PF dim, sorry. All right, and finally we're gonna have this dropout, and this is simply an end dropout. All right, so once we are done with defining all these layers, now we are ready to actually take in the to write the forward function, right? So the idea is we mentioned that we already have the input here, and we already do all this, right? Which will be handled by the encoder code here. But imagine that we have, every time it repeat this layer, right? What it's gonna do, right? So we imagine that we have this source, right? Which is batch size, source length, and is already converted in projected into hidden dim, right? And we also have this source mass, right? And the shape is batch size, 1, 1, and source length, right? And you may wonder, what is this source max? Well, it just if the token is panning, it will be 1, and otherwise 0, right? So it will be basically for applying to the attention, right? And you may wonder why we need this 1, 1. This is basically the shape of the attention here. So we can multiply with it, and we can so that's why the shape looks like this, right? And this will be made somewhere when we actually code it way down, right? So we don't have to worry about how we get this. Yep. All right. So once we get the input, what we're gonna do is that it's gonna apply the self.attention layer, self-attention, and then we pass in the tree source and the source mass, right? So what is this tree source? It's basically this tree arrow, right? 1, 2, 3, right? So we duplicate it 3 times to this self-attention module, which we need to code later on, along with the source mass, right? And then it's gonna return as the modified source, right? Which is this line, right? This black line here. And then along with also the one more thing that we don't really need, right? This we're gonna define what is this by in here, multi-head attention layer, right? But assuming that it returns two things, we only need the source, which is the part here. All right. And we have to the next thing what we're gonna do is we're gonna apply some addition here with the original one and also layer norm, right? So what we're gonna do is we're gonna say self attention layer norm, and we're gonna do self plus self dot dropout underscore source, right? So this part is basically coming out from the attention, and this is the original one, right? And then this is gonna give us source, right? And by now, let us make sure we understand the shape, right? So the shape is basically batch size, sorry, source line and hidden, right? Okay, so this is basically we are done with the first one, right? So you can see that if we assume that this is actually very easy, so easy to implement, so it's actually very easy, right? Now we're gonna send it to the feed forward and also add it and send it out, right? So I think this is also fairly straightforward, right? So we're gonna say source is basically equal to self dot positional basically self dot feed forward source. All right, and finally this is gonna be source equal to self dot ff layer norm source plus self dot dropout underscore source. All right, and the shape here is simply batch size, basically the same. All right, and then finally we return this source. All right, so that's done actually. So you can see that is not actually very difficult, right? This part, right? Of course, all the meat is in this thing, right? In which we have the code, but you will realize that actually it's not very difficult either, right? So yep, so we are done with the encoder layer, right? So now the next thing we're gonna do is basically the encoder itself. But before anything else, let me just run this code, and then it's not defined. So give me 1 second. From torch dot okay, import torch dot nn as nn, right? And I think by doing this, okay, now this one should run now smoothly. Okay, great. All right, so we are done that. Now we can close this encoder layer. Now we can work on this encoder. All right, so for this encoder, we're gonna repeat this encoder layer X time according to what user specified, right? And we also need to do this embedding and also positional embedding, right? And this is gonna be the whole encoder, right? So let us first code this encoder, right? And so we have to specify self.device equal to device, and self.token embedding equal to nn.embedding, input name, comma, hidden. All right, so this is basically the embedding here in this pink part. And then for the positional embedding, in the original paper, they actually use cosine, cos and sine waves, right? But here I think later on is very common to simply use a simple lookup embedding table, right? There's also research on something like relative positions, right? So that is something you may want to look at, right? So here we specify the max length to 100. That means that you're gonna have positional embedding for first token until the 100 tokens. So we assume that the maximum length is 100 for all the input, which makes sense because based on our data sets, our tokens is no longer than like 30 or 40, right? So 100 is more than enough, right? And then for the layers is simply nn.modulus encoder layer, head them, n heads, pf them, dropout, and device. All right. And then we're gonna have this. How many we need this for range and range based on n layers. Yep. So the users can specify how many they want this, right? So you can repeat this, come back again and again, right? And so yeah, I think that is pretty much the layers we have here, and then we're gonna do the dropout. And here is simply nn.dropout. Dropout. All right. So once we have defined everything, now we can do the forward function, right? So assuming that the source is simply batch size and source length. Oh, by the way, let me just do this to remove those errors. So you imagine that things come in and it's just source, batch size and source length, right? According to the data loader, right? And we also have this source mass, which is basically source length, right? And here is just the shape that match the attention. So now what we're gonna do is we're gonna now code this, right? So and it's very easy, right? So batch size equal to source.shape 0, and source length is equal to source.shape 1, right? And then what we're gonna do is position is equal to torch.arrange 0 to source length. All right. So this is basically gonna give me a numbers between 0 to source length, right? And then we're gonna squeeze 0, and then dot repeat this for batch size times. And then dot to self device. All right. So for those who are wondering for the shape, so the shape is simply batch size and source length, right? So for each of the batch, we're gonna have this position embedding that we're gonna add to the original source, right? And of course, through training, it will learn the correct position embedding, right? So what is the essence to capture for the first token, the second token, etc., right? So this is gonna be learned by the neural network, but in the beginning we just initialize a random embedding, and you're gonna learn what each position need to capture, right? And then we're gonna do is the source is simply equal to self.token embedding, right, of the source. Multiply with some scaled, self.scaled, and And this scale is simply self.scale equal to torch dot square root of torch dot float tensor hit dot two self dot divides. Yep. And for those who are wondering, why do we need to multiply once we convert to embedding? Why we need to multiply with self.scale, right? Well, once we multiply with this number, this embedding will be a little bit smaller, and the variance is a little bit scaled down, so that when you add with the embedding, there will be some very nice interaction. Otherwise, this will be too big, right? But of course, the papers did not really explain very well why do we need this. So feel free to experiment taking it out, and you can see the effect, right? And then so we're gonna have this, and we're gonna apply some dropout, which this is gonna give it some chance to learn whether some embedding may not be needed, right? So I think that should be it. Plus self dot position embeddings. All right, of the post, and then that's it. All right, and let me make sure. Yep, yeah, should be there. Okay, give me 1 second. Here should be here, and this should be here. All right. So first you do the self.scale, then you plus the embedding, and then finally you apply the dropout. All right, great. So this is simply this part. All right. So now once we have this, maybe we can write down the shape. Source is simply batch size. Source line, and hit them. Right. By the way, for those who are like Chucky, how do you know how to write this code? Right? Well, what you have to do is first the way I learn is that I go to a lot of GitHubs, try to get some inspiration how people actually code, right? And then when I actually code by myself, of course I look back and forth on the GitHub, but eventually you just need to code one by one, print out the shape, make sure they can be added. So there's a lot of like line by line coding, right? And so there's a lot of hard work behind. But of course, if you want to actually understand like every bit and detail, you have to do like that, right? That's just some encouragement. And then the next thing is simply for layer in self.layers. We're gonna apply this layer. Source and source mask. All right, and finally, once you pass it into a lot of layers, like many times, you get the source, all right? And finally, we can write the shape, right? The shape is batch size, source line, and hit them. You can see that is very nice, right? In every layer is always this shape, right? Which makes sure that we can always repeat this many times without some shape errors. And then finally, we return the source. All right. So I think that's it for the encoder. Let me just take a look for a few seconds to make sure that they are correctly written. Okay, great. So I'm gonna run this. All right, and now we are done with the encoder, right? So yep. So congratulations, we are done with this. And the next part is actually coding the multi-head attention layer, and also the position-wise forward layer of this module, right? I think why not we code the feed forward first, because the feed forward is actually a little bit simple, right? So let us go down here. So for the feed forward, well, what we do is simply self.fc1 is equal to nn.linear hit them, and PF them. So we project our source into, and then we also have FC2. PF them into some dimension that we want. All right. So you simply project it into some dimension and then project it back, right? So we hope that this feed forward layer can learn some interesting relationship, right? But eventually convert it back to hidden dim. Why? Because we need to send this to the decoder, right? And that expect the hidden dim, Yep. So now we are back. And we also have to code the dropout is equal to nn.dropout. All right. So now we can what we can expect from the input layer, or from the input, right? Well, we can expect that the input is simply batch size, sequence length, and hit them, but actually this is source length, right? And which is basically, if you look at the encoder, that would be the output from that, right? So so what we're gonna do is we're gonna say x is equal to self.dropout and torch.relu and self.fc1 x, right? And then finally x is equal to self.fc2 x, right? And finally return to x. Right? So yes, for this feed forward layer is actually quite simple, right? You just simply project it into PFNIM, project it back to HitDim, and that's it, right? Of course, there's some ReLU activation and dropout, right? So, but this is very similar to stacking layers, right? Before the next layer, you apply some ReLU so that you can learn some non-linear relationships. All right. So another congratulations, we're done with this fairly simple feed forward layer. We're gonna just run this one time. All right. So the next one is the multi-head attention. All right. All right. So for the multi-head attention, the idea is that there's this idea of scaled dot product attention, and the idea is very simple, right? You take the Q and the K and the V, right? For the encoder side, basically these are the same value, but for the decoder side, Q is from the decoder and K and V is from the encoder, right? But anyway, the idea is that you perform a matrix multiplication of Q and K, which is represented here, right? And then you divide it by some scale factor, right? And then you perform some softmax, right? And then finally, you matrix multiplication with V, right? Which is basically this picture, right? So that is the entire scale dot product attention. And in the big picture, multi-head attention is simply you send in V and Q, K and Q. You project it into different like number of heads. If you have 8 heads, you project Q into 8 of them. Each of them have 8 copies, and then you perform this scale dot product attention 8 times, right? So why do we want to do that? Well, by doing this 8 times, you are allowing so V, Q, K, and Q is basically the same tokens. They are basically the same copy of the sentence, right? By having them attending them many times, you allow them to capture different relationship, right? So maybe the first head may be focusing on part of speech. The second head may be focused on grammar. The third head may be focusing on code reference, etc., right? And then finally, to combine all this relationship, you can do a concatenation, and then finally a linear operations, right? All right. So to better understand this operation, why not we do some coding, right? Which is actually not that difficult, right? So In here, in the multi-head, what we're gonna first have, firstly, we're gonna make sure that hit them mod with n heads is equal to 0, right? Because here we're gonna divide them into number of heads, right? And so we want to make sure that they are divisible, right? And then we're gonna have hit them equal to hit them, and self.n heads equal to n heads. Self.head them equal to hit them n heads, right? So you can imagine that once we project V into some linear layer, they will be chopped. They will be chopped in the hidden dim, right? According to the heads, right? So this chopped version of this V will be a head dim. And then we also need to define this linear layer right here, right? Which is simply self.fcq. This is for the Q, is nn.linear. Hit them. And we're gonna do this for similarly for K and V. Right. So this is simply the linear layer here, right? And then we also have self.fco, right? And then dot linear. Hit them. All right. And if I'm not wrong, this FCO is basically this linear layer, right? And then of course we have self.dropout equal to nn.dropout. Dropout. And then the self.scale equal to torch.square root. Torch.float tensor. This is basically the same thing as about self.headpin .2 devices. Yep. So this part is basically the denominator here. All right, so I think we are done. So yep, this is DK, right? So DK is basically head dim, right? So I think that's perfect. Yep. So I think that is all the things we need. Now we can take the forward function, right? So even though we name this query key value, right, you have to know that this is basically the source tokens, right? So even though we name it differently, they are basically the source tokens, right? But what we're gonna do is we're gonna do firstly batch size equal to query.shape 0, and what we're gonna do is we're gonna send this VQK to the linear layers. So Q equal to self.fcq, and we're gonna do this for also K and also V, and here is K and also V, and this is key, and this is value, right? And again, you have to understand that when I send them, they are basically source mask, right? So this three are basically the same thing, right? But once we project them, so what does this projection do, right? This projection is basically project them into some useful, interesting information, right, that the neural network can learn. And how do they know what are the useful information? Well, the backpropagation gonna take care of that, right? And then so once we project them, Q equal to K equal to V is the dimension is basically batch size, source length, and hit right? So now what we're going to do is we're going to now chop them, right? And the chopping looks a little bit scary, but it's simply batch size -1 self.nheads self.head them. Right. So what are we essentially doing is that we take the batch size and we take the hit them and split them into n heads and head them. So this multiply this will equal to this, and so will be right here, right? And then we're going to do some permute 0, 2, 1, 3. So based on this, the shape is basically batch size and heads, area line, and then head them. All right. So we swap the heads into here, right? And we're gonna do this for K and V2, right? So this is K, and this is V. All right. So yep. So basically, that's it, right? So now we are done in here, right? We already chopped them. Now we are ready to send it into this purple. This is purple color, right? Purple, right? In which you do the math move, basically QK, Q times K, dot product with K divided by scale factor, softmax, and V, right? So this is actually quite easy to do. I would say my first time implementing this, what makes me so confusing is the shape, right? So what you can do is basically try to randomize some value, try to view them, and see what happened in a very smaller data, and you can understand them. All right, so you can see energy is basically torch.matmove, Q and K dot permute 0, 1, 3, 2. Right, we permute so that they can be actually dot product together, and then finally divided by self.scale. Right, and so what is this, right? So this is simply this one dotted with K, right? Which is batch size and heads, head them, and query the key length, right? All right. So once we do that, the energy is nothing but batch size and heads, query length, and then the key length, right? Because this head name and this head name will be canceled. Right. So this energy is simply this part, right? So very straightforward. And then once you do that, we're gonna apply some mass. If mass is not none, right? We're gonna make sure that we fill the mass so that any attention on the padding will be very small. Mass filled. Mass is equal to 0. So any number with 0 will be filled with a very small number. Yep. Right. So this is for masking for making attention to padding at 0 to 0. Yep. So that is basically what this this code do. And then once we have that, what we're gonna do is we're gonna now softmax attention equal to torch.softmax energy, and then dim equal to -1. So this softmax is basically this softmax. And so once you softmax this, this gonna be basically the same, still the same shape, but things will be smaller, right? I mean, they will be squeezed into zero, like in a smaller range, right? In a normalized range. So yep, I think that's it. Now, once we do the softmax, according to here, you need to multiply with, I mean, dot product with V, right? So what we're gonna do is we're gonna say torch dot maximum between self dot dropout tension with V, right? And that is X. Okay. And attention is this one, right? And so attention is this one, and dotted with V, right? And V is simply the same as Q here, right? But here is a value length, right? So so once we do that operation, we're gonna have only the query length, right? Because this value length and this will be cancelled out, right? So now once we do that, X is equal to batch size and heads, query length, and then head. All right. So once we are done with that, now we can permute a little bit. X equal to X dot permute 0, 2, 1, 3 dot contiguous. Yep, contiguous is very trivial. It makes sure that once we do contiguous, we can perform a function like dot view, right? But if you can't do dot view, you can always use a dot reshape. Yep. So here is simply that, right? And once we do that, now we can do X equal to X dot view size -1 self dot hit them, right? So, and then finally we're gonna do, so you write here X is equal to that size query length and then hit them, right? So what is this happening, right? You can imagine that this is simply similar to this concatenation function, right? In which you combine everything, but because we already have this 2 dimension, we just combine them. It's already like a concatenation. Yep. And then finally we can do X equal to self dot FCO X query line. What we're gonna return is the X and the. Yep. So yeah, it's a little bit lengthy, but actually very straightforward, right? So we project them into a linear layer, we split them into heads, we do the QK divided by DK, square root of DK, apply some mass, softmax, dot with V, and then finally we take some reshaping, right? So that we can apply the F's, the linear layer, right? And yeah, I think that is pretty much it for the multi-head attention. Yep. And let's run this. All right, great. So now we are done with this multi-head attention. All right, so now I think we are now ready to actually code the decoder layer. So the decoder layer is simply the gray part here, and if we understand that we send it into mass multi-head attention, add norm, and we take the encoder outputs as a key and value, and here is a secure query, and then just basically the same multi-head attention we did previously. So a lot of the code is basically the same. If there's one part that is different, is first is the mass here. So we have to mask the attention forward, because you don't want the current token to pay attention to the future tokens, right? Otherwise it's cheating, right? Because you want them to predict, right? But if you can see the next token, you can basically just copy that token and get always the best performance. Then it's not going to learn anything, right? The next part that is different is probably here, right? In which the Q is from the here, but the K and V is actually from the encoder, right? So the idea is that if you take the output, the translation as a query, you want to ask which token in the original input should I pay attention to, right? So that is the meaning of Q and K and V here, all right? So that is the idea. All right. So without further ado, why not we just code this decoder layer so to create more understanding, right? So so a lot of the things, if it's the same, I will not talk too much about it to save time. I really don't want this to be a very long video to bore you guys. Yep. In the future videos, if it's possible, maybe once I feel that you guys are quite comfortable with coding, we can make the video shorter and more about explanation, right? Rather than me code by line, and I think that would be, but that would make more sense later on, not right now. All right, so we have here 3 layer norm, right? So 1, 2, 3, all right. So that would be a 3 layer norm. Now we have the attention. Multi-head attention layer, what we already coded. Hit them and heads. About, okay, make it smaller a little bit, and device. And this one is the encoder attention. It's basically the same, right? So this one is for this self attention, and this encoder attention is probably for this part, right? And then I'm gonna say solve the position, solve the feed forward. Is equal to hidden, and trouble. All right, so we have all the components for our decoder layer, right? So once we have all the decoder, once we have all the components, then I think we can put pass here, so there will be no errors here. So we take in the target, which is batch size, target length, and hit dim, right? So this is the actual translation. We also have the encoder source, right? Which is so this is basically from passing to the encoder, encoder, right? So this is the actual thing that is already encoded through several layers of encoder. And this is the mask for target, and this is the mask for source, right? So this is basically making sure that the attention is not paid on the padding. But for this mask, is basically making sure that you don't allow the attention to give on the future token, right? So this is a very actually a very cool technique, I would say. A very simple technique, but very cool technique. Yep. So what do we do next? First thing is we send to the so we're only coding the gray part here, right? So we send to the attention first, right? So the equal to self that attention. Right. So this is basically copying three guys and then do QKV and right here. And we also have this mask, right, to make sure that to make sure it doesn't pay attention to future tokens. Yep. So this mask is specifically for targets. Yep. Note that this source mask is for masking the padding, but this is for masking the future tokens. So they are different, but they can be used same in the multi-head attention, because we say that please mask anything that is one, right? So we can play around with this. And then what we're gonna do is we're gonna do self dot attention layer known is target plus self dot drop off. Yep. And then this is the TRG. All right. So this is simply this part, right here, add nom. So that's, I think that's it for this part. So we can take a look at the shape. The shape is batch size, target length, and hit them. Yep. Okay. All right. So now once we do that, now we can do this upper part. So what we're gonna do is we're gonna say attention equal to self dot encoder attention, and this is Q, right? QKV. So the K and V will be the encoder source, right? So this is very important, all right? Make sure you. So this is QKV, right? So during this part, the K and V's come from the encoder, and the Q come from the decoder, right? Which is this one. And then we send in the source mask. All right. And then what we're going to do is, again, we're going to apply the layer norm. All right. And this one will remain the same shape. Yeah, it's very nice of transformer, right? Once you code it, you will see that they are very consistent, right? Like it's same shape even after some operation. Yeah, this allow us to repeat this many times. Yep. And then what we're gonna do is send to what do we need to do this? We send in the feed forward and add nom. Yep. Give me 1 second. So yep, you add norm again here, right? So TRG, sorry, minus, yeah, underscore. Yep. And then so right here the shape is still the same. But notice here that I actually take the attention, right? Usually I make it underscore, but here I take the attention simply so that I can know how the output and the input are related, right? So this attention gonna capture that. And we're gonna use that to return the target and also the attention, which we're gonna visualize it later on. But yep, and we're gonna also write the attention shape. The shape of the attention is batch size and heads, target length, and source length, right? So it makes sense, right? It basically just say that for this head, which target is a pair, right? Like target, how much attention is paid pairwisely of the tokens in the target and the source, right? All right, so I think that's it for the decoder layer, right? So I think not so difficult, but definitely a little bit of coding, right? All right, so now we are done with the decoder layer. So now we can close it down. Now we are ready to actually code the decoders, right? And I guess the decoder is simply coding everything as one and not so difficult, right? It's because we already code once for the encoder. So I gotta quickly do this and make sure we don't spend too much time here. I have to be careful here. All right. Okay, and this is okay. Great. Just give me 1 second. I want to make sure that my bracket is actually outside of this. So let me just go to the encoder to make sure that no. So this must be here. All right. Yep. So this is basically like a list of encoder layers. Yep. I think that's it. Run this one time. Yep. And now we are coming back to the decoder. So for this, okay, great. So I think this is correct code. Now we're gonna have also the FCR. Yeah, but if you understand the encoder, basically this is all the same, so I don't explain too much to waste your time. I just coded once, and I think you'll probably understand everything. plus square root. Okay, great. Okay, so once we have everything, now we can write the forward function, and we expect that we have the target right in here, which is simply batch size and target length, right? Of course, along with the encoder source, and this is basically from the encoder side, and this is the mass, right? So for this, we have to simply do batch size equal to target.0, target length equal to 1, and then position. I think this is basically the same, right? Arrange 0 target length dot unsqueeze 0 dot repeat batch size comma 1 to solve the rest. This is blank. So this is for the embedding, and I'm going to do target is equal to self.token embedding, target and self.scale plus self.position embedding plus, and everything we're going to apply self.drop off. Yep. And this is the shape is target length and hit them. And then here we just say for layers. So right here we just do this part, right? And then we're just gonna for loop here, and then we linear layer and softmax. Yep. For layer in the cell layers, target attention equal to layer, and again text target and source target mass and source mass. So right here the shape is batch size, target length, and hit them. Similarly, attention here is batch size and heads, target length, and source length. Finally, what we're going to do is output is equal to self.fcout and target. Yep. So that is the last part here, the linear. So output equal to size, target length, and output. Yep. We don't really have the softmax here because for the softmax, the cross entropy loss already do it for us, so we don't really have to do that. Return output and attention. Yep. So yes, I think that's it for the decoder. Very straightforward, and that looks very much like the encoder, right? So we're gonna hit enter and make sure it's gonna run. Okay, great. All right, so now I think we can close this. And now I think that's it for what I'm gonna code. And to make this tutorial shorter, I think the rest we can just use the code that I have already prepared, right? So now we're gonna put everything together, the encoder, decoder, and then put it into a SIG to SIG model, right? One part that I have to mention is about the the target mask that I have told you. So what I can do is be simply like this, right? In which for the first token, it can only pay attention to the first word, which is itself. For the second token, it can only pay attention to the previous word and itself, right? So we can do this using a function called TRIL. Basically, I think it's related to triangle above triangle, something like that, or lower triangle. Yes, lower triangle. Yep. And then we're gonna add this mask with the padding mask. Yes. So if this is also a padding, then this is gonna be also set to 0, right? Like this, right? So there will be added the target mask and the source mask, yeah, which is something I have to mention here. Otherwise, the rest is very straightforward, right? So here is the source mask, right? This is very simple about the padding, and for the target mask, I just simply use the lower triangle to create those things, and then finally I do some and, right, so that you can get the final target mask. And then in the forward function, what I do is very simple. Make the mask first, and then send it to the encoder, send it into the decoder, and then output the attention, right? So very straightforward. All right. So I think we are done on this part, right? And to make sure that things are very consistent, why not we stop here, and then we're gonna run everything from the right to make sure that things all run in the nice order. Yep. Okay, great. Okay, so now we can actually do the training, and here is something that you already are very familiar with: initializing weight, initializing a lot of parameters. Here I'm using only 3 layers of encoder and decoder. In the papers they use like 8 or 6, right? So you can use as much as you want, but it's going to take a lot of time. And I initialize the encoder and decoder, all right? And also then all right, I think I have a repetition of this. Okay, anyway, and then this is the sequential transformer, right? And then so my model is quite big, right? This is 8 million parameters model, right? And cross entropy and the criterion. And then of course, the next one is the training loop. And there's one thing I have to mention is that for the input, you want to shift the input to the right, because you want to always predict the next token. So definitely this is something you have to take note of. Otherwise, the training is very straightforward, right? So for the training loop, it's you send to the GPU. You send to the GPU, and you try to take out the EOS, and then when you actually take the output, you compare with the shifted version of the shifted right version, right? And then criterion, there's some clip norm, right? And then similarly, I'm just going to run this. And similarly, we also have for the evaluation, right, which is very similar. And then of course, we have some helper function that we have just like previously. And finally, we have this thing, right? Before I actually run it, maybe just run one epoch and see whether there's any error, right? So let's run this. All right, so it seems like there's no really any errors, right? If so, then I'm gonna just interrupt this, right? I'm just gonna let it run. Maybe I can let it run, right? But to not wait too much, I will open what I have already trained in the 06, So we can actually come down here. So you can see that I have trained for 10 epochs and the loss is slowly going down. And the perplexity is also getting down. And these are some figure of the train loss and validation loss. And of course, this is my the testing set. Of course, I can also test on some random news. And I'm gonna just let you guys take a look in this file later on. And you can see that it's actually predicting, hopefully it's predicting correctly, I think. All right, so you can see that that it looks quite good. Yep. And then of course you can always print attention. So I already give you some instruction how to actually look at the attention. So feel free to take a look. Right. And you can actually now display the attention, right? So you can see Jung, I'm not sure, this is Junke, is young, right? Bebe is white, right? Fran is outside. I'm not sure that is correct, but this is definitely correct, right? Nahi and Nia, right? So you can see that the model is actually learning a lot of relationships between the input and the output, right? Yep. So yep, I think that's the transformer. Thank you very much and see you in the next tutorial. Bye-bye.